Let's compare some of the operating variables of an actual power cycle to that of a reversible power cycle. A power cycle receives 1,000 BTUs by heat transfer from a reservoir at 1,000 degrees Fahrenheit, and it discharges energy by heat transfer to a reservoir at 300 degrees Fahrenheit. The thermal efficiency of the cycle is 75% of that for a reversible power cycle operating between the same reservoirs. For the actual cycle, determine the thermal efficiency and the energy discharged to the cold reservoir in BTUs. Repeat for the reversible power cycle. Okay, so here's a schematic of the problem statement. We have a high temperature thermal reservoir operating at 1,000 degrees Fahrenheit. There's a second reservoir, a cold reservoir, operating at 300 degrees Fahrenheit. The power cycle is in between. 1,000 BTUs of energy is moved from the hot reservoir into the power cycle by heat transfer, and work is produced. And then there is some portion of the 1,000 BTUs which is rejected to the cold reservoir. So here's what we're given. We know that QH is 1,000 BTUs. And we know that the efficiency was given as 75% of the theoretical maximum. Well, let's calculate the theoretical maximum, but to do that, I have to work with absolute temperatures. So here we have Fahrenheit temperatures. We need to add 460 to each and get the temperatures in degrees Rankine. So the hot temperature is 1460 Rankine, and the cold reservoir operates at 760 degrees R. So we know that the maximum theoretical efficiency of a power cycle depends only on the temperatures of the reservoirs. So we have 1 minus Tc over Th, and we can calculate that the maximum theoretical efficiency of this power cycle is 48%. But the actual power cycle operates at 75% of that, so the actual efficiency is 36%. So let's find the work output of the power cycle. We know the efficiency is just work divided by the heat input. We can rearrange this and say that work is efficiency times QH. And the efficiency we calculated to be 36%. QH was given as 1,000 BTUs. So the work output of the actual power cycle is 360 BTUs. Well, what is the work output of the reversible cycle? Well, the work output of a reversible cycle is just the maximum theoretical efficiency times the heat input. Well, we know the maximum theoretical efficiency based on the reservoir temperatures was 48%, and that 1,000 BTUs of energy was transferred into the power cycle. So the work output of a reversible power cycle is 480 BTUs. Now let's find the heat transferred to the cold reservoir, and this will do for the actual cycle. Well, an energy balance yields that's just W is QH minus QC. So let's rearrange solve for QC, which is QH minus W. Well, QH is given, and we calculated the work for the actual cycle at 360 BTUs. So that gives us a value of QC of 640 BTUs. Now, there's another way we could have done this. We could have looked at the efficiency equation, which is just work over QH, and work is QH minus QC. This reduces to 1 minus QC over QH. And so we say that the efficiency is 0.36, but that's equal to 1 minus QC over QH. I can rearrange this term here and get that QC is 1 minus 0.36 times 1,000 BTUs. And I'll get the same answer. QC is 640 BTUs. Let's calculate the heat transfer to the cold reservoir for the reversible cycle. Well, for a reversible cycle, QC is just QH minus the work done by a reversible power cycle. So QH was given as 1,000 BTUs. The work of the reversible cycle we calculated to be 480 BTUs. So QC, or the energy transferred from the power cycle to the cold reservoir, is 520 BTUs. We could have calculated this yet another way by looking at the equation for the maximum theoretical efficiency. It's normally given as 1 minus Tc over Th, but for a reversible cycle, Tc over Th is just Qc over Qh. So we know that the maximum theoretical efficiency was 48%. So that's equal to 1 minus Qc reversible, which is what we're looking for, divided by QH, which is 1,000 BTUs. And so we get QC for a reversible process is 1 minus 0.48 times 1,000 BTUs. And we get the same value as we did with the other way of doing it, 520 BTUs.